Leak Detection System Tutorial, Part 1. Requirement for leak detection. The deployment of a leak detection system, LDS, for pipelines is increasingly seen as essential due to heightened awareness of environmental, safety, and socio-political risks associated with fluid releases. As public scrutiny and regulatory expectations intensify, pipeline operators are under greater pressure to ensure that any failure or breach is rapidly identified and addressed. A properly implemented LDS plays a critical role in limiting the consequences of such failures, supporting not just technical safety but also operational credibility and environmental stewardship. And LDS enables rapid response to leaks, minimizing potential harm to people, the environment, and assets. Whether the consequences are economic, such as product loss and downtime, or more intangible, such as public outrage or reputational damage, the ability to detect and act on a leak promptly is indispensable. By reducing detection time, an LDS becomes a core component of emergency preparedness and response, especially in high-risk or environmentally sensitive locations. Importantly, LDSs are not preventive tools. They are reactive safeguards. Therefore, they must operate in conjunction with systems that monitor pipeline condition and prevent degradation, such as corrosion monitoring, cathodic protection, and regular inspection programs. Together, these systems fulfill the ALARP as low as reasonably practicable principle, ensuring both the probability and consequences of a leak are minimized through a combination of prevention and detection. While few regulatory frameworks explicitly mandate LDS installation, many impose general requirements for pipeline safety, environmental protection, and risk management. The global trend is toward performance-based legislation, particularly in Europe and North America, where operators must demonstrate the effectiveness of their risk control measures. In this context, LDSs serve as verifiable and auditable systems that support compliance and help secure necessary permits and authorizations. LDS implementation should be automatic in specific situations. First, when legislation or local codes mandate leak detection, full compliance is required, concessions notwithstanding. Where minimum regulatory requirements fall short of modern best practices, SCADA-based LDSs should be considered to bridge the gap, provided the legal minimum is still met. Second, pipelines equipped with remote monitoring and control via SCADA or DCS must incorporate LDS capabilities, either fully integrated or standalone with real-time data connectivity. Third, when risk assessments show that leak detection significantly reduces failure impact, especially with hazardous products, a suitable LDS must be provided. Product characteristics and environmental exposure strongly influence LDS applicability. Pipelines carrying volatile, toxic, or flammable products such as LPG, NGL, MOGAs, ethylene, or sour gas require systems that emphasize short response times and high robustness. In such cases, even minor leaks pose disproportionate safety hazards. Likewise, pipelines running through sensitive or protected environments must prioritize high sensitivity and precise leak localization to minimize ecological damage. The design of the LDS should consider the pipeline's operating conditions, location, and associated risks. For example, high-consequence areas near urban populations, water bodies, or critical infrastructure demand more sophisticated detection capabilities. Fast detection and accurate location tracking are essential not only for mitigating immediate hazards, but also for facilitating rapid repair and cleanup, thus reducing long-term environmental or financial liabilities. In scenarios where none of the regulatory, operational, or risk-based triggers apply, the installation of an LDS should be considered on a case-by-case basis. Factors such as public visibility, corporate reputation, insurance requirements, and stakeholder expectations may justify the additional cost. Cost-benefit evaluations should weigh the long-term advantages of enhanced safety and reduced incident impact against the upfront and lifecycle costs of the LDS. In summary, the requirement for leak detection must be treated as a strategic engineering decision, influenced by legal mandates, technological capabilities, risk assessment outcomes, and broader operational goals. Whether required by law or driven by good practice, an LDS is a fundamental part of pipeline integrity management, providing measurable value in safety assurance, regulatory compliance, environmental protection, and public confidence. Leak Detection System Tutorial Part 2. Performance Indicators for Leak Detection. The effectiveness of a leak detection system, LDS, is defined by key performance indicators that collectively determine how well the system performs under real operating conditions. These indicators are critical for selecting, configuring, and maintaining a reliable leak detection strategy. Each parameter, sensitivity, reliability, accuracy, location capability, robustness, and cost, must be evaluated in context to ensure that the LDS meets the operational, safety, and environmental expectations of the pipeline it serves. Sensitivity is the measure of how small a leak the LDS can detect and how quickly it can do so. It is typically expressed as a combination of minimum detectable leak size and the corresponding response time. While high sensitivity allows for early detection of even minor leaks, overly aggressive settings can increase false alarm rates. A balance must be struck between sensitivity and operational practicality, especially in pipelines with fluctuating flow or pressure conditions. Systems that are too sensitive to normal transients can lead to alarm fatigue and erode operator trust. Reliability refers to the LDS's ability to accurately distinguish between true leak events and benign operational variations. A reliable system consistently detects real leaks without generating frequent false positives. Reliability is primarily a function of the leak detection software and algorithms, independent of external hardware performance. However, it is highly sensitive to signal quality from instrumentation. Systems that rely on model-based calculations may require frequent recalibration or tuning to maintain reliability, especially in pipelines with changing operating profiles. Accuracy concerns the system's ability to quantify the leak rate and, in some cases, estimate the total volume lost. Some systems can also calculate leak location and direction. These capabilities vary depending on the detection method used. For example, simple mass balance methods may provide a general indication of leak presence but offer limited information about location. More advanced compensated methods or statistical systems can improve measurement precision, but this often comes at the cost of system complexity and maintenance demands. Leak location capability is particularly important for long-distance pipelines where visual inspection is impractical or time-consuming. The ability to quickly pinpoint a leak allows for targeted shutdowns and faster response, minimizing environmental damage and operational downtime. Location accuracy is often proportional to the number of instrumentation points and the quality of the data. Techniques such as negative pressure wave detection or statistical flow analysis can narrow down the leak position to within a few percent of the pipeline length, assuming optimal sensor placement. Robustness is the LDS's resilience to changing conditions and data quality issues. A robust system continues to operate reliably during power outages, signal dropouts, or transient process events. It must also tolerate fluctuations in product composition, temperature, or flow without misinterpreting them as leaks. The distinction between reliability and robustness is crucial. Reliability pertains to performance under ideal conditions, while robustness measures the system's adaptability to real-world variability and imperfections. Cost must be viewed not only as initial capital expenditure, but also as the total cost of ownership. This includes installation, instrumentation upgrades, software licenses, calibration gas, tuning, periodic testing, and ongoing maintenance. Operator training and false alarm handling also incur indirect costs. A low-cost system that generates frequent false alarms or requires constant manual intervention may ultimately cost more over its lifecycle than a higher-priced but more stable alternative. Trade-offs between these indicators are inevitable and must be carefully evaluated. For instance, increasing sensitivity may decrease robustness unless supported by advanced filtering algorithms. Enhancing accuracy might require additional instrumentation, impacting cost and installation time. Therefore, system selection should be based on a prioritized list of performance requirements tailored to the pipeline's specific risks and operational characteristics. An LDS should not be judged solely by its theoretical performance, but by how consistently it performs in practice. Performance benchmarking during commissioning and periodic validation in the field are essential. Operators should conduct blind leak simulations or data-driven testing to verify system response under realistic conditions. Over time, trends in false alarm rates, Missed detections or tuning adjustments will reveal the LDS's true capability and reliability. In conclusion, the performance indicators of a leak detection system define its effectiveness and operational value. By carefully balancing sensitivity, reliability, accuracy, location precision, robustness, and cost, pipeline operators can select and maintain an LDS that delivers actionable data, minimizes risks, and enhances the integrity and safety of the pipeline over its entire lifecycle. Leak Detection System Tutorial Part 3. Selection of a leak detection system. The selection of a leak detection system, LDS, must begin with a clear understanding of its primary function: to detect the presence of a leak as quickly and reliably as possible. This primary requirement should guide all technical decisions, from system architecture to instrumentation selection. Among the available technologies, corrected mass or volume balance methods are most widely recommended due to their simplicity, effectiveness, and compatibility with SCADA-based systems. Integration with the pipeline's control infrastructure, whether via direct embedding into the SCADA system or through real-time communication with a standalone LDS platform, ensures continuity, responsiveness, and ease of operation. Reliability and robustness must be treated as non-negotiable characteristics when selecting an LDS. These two performance attributes ensure consistent operation during both steady-state and transient conditions and reduce the likelihood of false alarms, which can undermine operator confidence. While high sensitivity and detailed accuracy are valuable, they should not be prioritized at the expense of a system's dependability. A well-selected LDS should operate transparently in the background, issuing alarms only when credible evidence of a leak exists. Beyond basic detection, secondary functionalities should be evaluated based on operational and environmental context. Leak location identification becomes essential when the pipeline spans long distances or environmentally sensitive areas, or when isolation valve strategies are employed. Locating a leak enables selective shutdowns, reducing the extent of disruption and preventing unnecessary depressurization of unaffected pipeline sections. The value of this feature increases proportionally with pipeline length and the complexity of the network. Another critical secondary feature is static leak detection. Pipelines are often operated in a shut-in condition with residual pressure held within the line. Under such conditions, leaks can still occur and must be detectable even when flow has ceased. Static detection systems require careful sensor placement and pressure stability, particularly in lines carrying liquids close to their vapor pressure. These systems provide valuable assurance during maintenance outages or scheduled shutdowns. Batch tracking is an important consideration for pipelines that transport multiple products or varying compositions of the same product. In these applications, fluid interfaces must be monitored to prevent contamination, and any loss of containment can have disproportionate economic and operational consequences. LDSs with batch tracking capabilities help correlate product movements with potential leak events, enhancing both detection accuracy and situational awareness. Operator training features embedded in some LDS platforms also add significant value. Systems that offer simulation or replay capabilities allow operators to practice leak response under realistic conditions. These training tools can also be used during commissioning and audits to demonstrate preparedness and system familiarity. Simulation-based training ensures operators understand both the functional behavior of the LDS and the correct response procedures, reducing human error during real leak events. In addition to integrated SCADA-based systems, certain locations may benefit from supplementary detection systems. These enhancements, such as localized acoustic monitoring, hydrocarbon sensing cables, or smart sectioning valves, can be deployed in high-risk areas like river crossings, aquifers, or densely populated zones. Supplementary systems offer higher spatial resolution or faster response for specific leak scenarios and are especially valuable where a generic LDS may lack precision or coverage. Smart line brake valves, LBVs, represent a proactive approach to leak containment. When paired with a SCADA integrated LDS, these valves can automatically isolate pipeline segments upon detection of a major rupture or pressure anomaly. While LBVs require careful tuning to avoid premature closures, they significantly reduce spill volume and response time in the event of catastrophic failure. Their deployment is often justified in high-stakes environments where delay is not acceptable. In conclusion, selecting the right LDS involves more than choosing a leak detection algorithm. It requires a system-level perspective that considers the pipeline's design, operation, environment, and risk profile. The chosen solution must be functionally appropriate, scalable, and robust enough to maintain performance over the long term. With correct selection and configuration, the LDS becomes a silent but critical safeguard in the broader framework of pipeline integrity and risk management.